And we're back for another installment of Good News Read to You, number 4. My name is V. Happy to be here. We have 5 articles today. First of which is a healthier global diet could cut farm emissions by 85% on ScienceDaily.com. First stated source is London School of Hygiene and Tropical Medicine, and the journal reference Gibson et al. Food systems transformation would reshape global architecture in Nature. Number 2. How the heart's little brain helps it function and protects it against stress by Paul Arnold on medicalexpress.com. With a publication detail of Qian J et al. The intrinsic cardiac nervous system is essential for cardiac function and survival. Cell. In Cell. The journal. Cell. Third of which is first 3D nanoscale maps of human airway epithelium reveal hidden architecture of lung defense cells. On phys.org, stated author is Queen Mary, University of London. You go, Mary. Publication details. Let's do this. Vijaya Kumaran. Aran Vijaya Kumaran et al. 3D nanoscale reconstruction of human airway multiceliogenesis reveals cellular architecture remodeling and cilia mitochondria link via rootlets. Very exciting. In Cell Reports. Number 4. Tracking ion movement in porous carbon electrodes to boost energy storage and water desalination on Tech Explore. First stated author, Suzanne Sika, Leipzig University. Publication details. And it's a lot of middle initials. Henry R.N.B. Eninful et al. Asymmetric multi-site ion exchange in porous carbon electrodes in Advanced Energy Materials. Lastly, universal structure of exceptional points revealed in nonlinear light-based systems by Paderborn University on phys.org. Publication details Nai Hung Kwong et al. Universal topology of exceptional points in nonlinear non-Hermitian systems. Nature Communications. Oh, just one moment. All right, let's do this. Now, a healthier global diet could cut farm emissions by 85%. A worldwide shift toward healthier diets, more efficient farming, and far less food waste could fundamentally change what farmers produce and how agricultural land is used by 2050. New modeling suggests that Following these recommendations could reduce global farmland use by as much as 6% compared to current trends. I feel like it might be a typo. I feel like that's a typo, at least compared to the title. Anyway, the summary says a global shift towards healthier diets could sharply reduce livestock farming, free up agricultural land, and cut emissions from land use change by 85%. So, oh well, we'll run with it. We'll go with it. At the same time, the total value of livestock production could fall by 42%, or 630 billion US dollars compared with 2020. Fewer herds and more plant foods. The biggest changes would occur in the production of ruminant animals, beef cattle, sheep, and goats. By 2050, the global value of this sector could decline by an estimated 70%, 274 billion US dollars, with roughly 400 million fewer ruminant animals worldwide than in 2020. Plant-based food production would move in the opposite direction. The combined global value of vegetables, fruits, nuts, and legumes could rise by 57%, or 890 billion US dollars. Legumes include foods such as beans, peas, lentils, and chickpeas. Chickpeas are beans, garbanzo beans. These crops are important sources of protein and fiber and generally require fewer resources to produce than many animal foods. The findings come from an analysis published in Nature by researchers from the London School of Hygiene and Tropical Medicine, or LSHTM, Cornell University, and 10 modeling teams. The researchers examined what could happen, if the world pursued a food system transformation similar to the one proposed by the 2025 EAT Lancet Commission. Potential health and climate benefits. The 2025 EAT Lancet. Don't do that. Commission report concluded that a worldwide transition to healthy diets could prevent 15 million premature deaths every year. Why is that funny? Earlier research has also estimated that the global food system creates 10 to 20 trillion US dollars in hidden costs annually. These costs include healthcare expenses, environmental damage, lost productivity, and other consequences that are not reflected in the price consumers pay for food. Most of the estimated burden has been linked to unhealthy diets. The new modeling indicates that the recommended transformation could also sharply reduce agriculture-based net CO2 emissions from land use change. By 2050, these emissions could be 85% lower than they were in 2020, not to mention the methane. Land use change includes activities such as clearing forests, converting grasslands, or draining wetlands to create agricultural land. These changes can release large amounts of stored carbon into the atmosphere. Net emissions account for both the carbon released and the carbon absorbed through changes in land use. Now imagine if these plant-based or plant-centric food systems incorporated the indigenous practices and knowledge discussed in the previous video. A major disruption for farmers. Dr. Matt Gibson, lead author, who began the work at Cornell University before joining the London School of Hygiene and Tropical Medicine, LSHTM, said, transforming food systems would deliver enormous potential benefits to our health and the environment, but, as our results make clear, they would also lead to fundamental changes to global agriculture and affect the lives of millions of farmers and food producers. Rather than using these results as an excuse for inaction, it's critical that governments rise to the challenge and make difficult decisions for the good of our health and the planet. This means confronting powerful groups that profit from the status quo and a global food system that currently fails both those who produce our food and those who should be nourished by it. The findings suggest that the transition would not simply be an environmental or public health initiative. It would also create sweeping economic changes, with some agricultural industries shrinking while others expand. Daniel Mason de Croix, study co-author from Cornell University, said, "We should consider these scenarios not as a forecast of what will happen, but as a useful early guide of where challenges and opportunities may arise, which sectors would need to contract, and which would need to expand. A transformation of this magnitude cannot begin in 2050. Foresight modeling like that highlighted in this study is a valuable tool to inform actions today for more sustainable, healthy, and just food systems tomorrow." Foresight modeling is used to explore possible futures rather than predict one exact outcome. By testing different assumptions, researchers can identify where economic disruptions, policy challenges, and new opportunities may emerge. Uneven effects across the world. The economic effects would vary substantially between countries and regions. In the United States, the total value of agricultural production could fall by 21%, or 76 billion US dollars, by 2050 compared with 2020. However, the value of US crop production could increase by 20%, or 40 billion US dollars, while livestock production value could decline by 73%, 116 billion US dollars. India could experience a very different outcome. Its total agricultural production value could rise by 46%, or 198 billion US dollars. Crop production value could increase by 65%, or 208 billion US dollars, while livestock production value could fall by a comparatively modest 8%, or 10 billion US dollars. Just going to say dollars. Europe could see its overall agricultural production value decline by 35%, or $190 billion. European crop production value could decrease by 8%, or $22 billion. Billion US dollars. I'm going to keep saying it like that. While livestock production value could fall by 66%, 168 billion US dollars. These regional differences reflect variations in farming systems, current diets, production costs, land availability, trade, and the types of food each region produces. Changing diets would not be simple. Excuse me. The researchers assumed a costless consumer preference shift toward healthy diets. i.e., people changed their behavior to demand healthier diets. In other words, the models assumed that consumers would willingly change what they eat without accounting for the financial, cultural, or practical barriers that could make such a shift difficult. In reality, healthy foods may not be equally affordable or accessible everywhere. Dietary choices are also shaped by local traditions, personal preferences, income, food availability, and broader cultural ad- attitudes, not practices. The researchers emphasized that the scenarios represent only a selection of many possible futures. Additional studies will be needed to explore other pathways, including transformations based on different policy choices, economic conditions, and patterns of consumer behavior. The authors argue that bold policy decisions made now could help protect vulnerable food producers and consumers as agriculture moves toward healthier and more sustainable diets. Without careful planning, the benefits of the transition could be accompanied by severe economic disruption for communities that depend heavily on livestock and other sectors expected to contract. Ooh. Think of the methane. Now, how the heart's little brain helps it function and protects it against stress. For years, scientists have known that the heart has its own network of nerves, the intrinsic cardiac nervous system, or ICNS, sometimes called its little brain. It's like low-key condescending. Heart's little brain. Oh my goodness. Exactly how it functions has remained something of a mystery, but a new paper published in the journal Cell sheds light on how these heart nerves work to keep the heart beating steadily. The heart's nerve cells fine-tune signals coming from the brain to control heart function, including heart rate. But because they are so few, doctors have struggled to determine exactly what they do. A bunch of doctors are like, oh no. We might be doctors, but we don't know what they do. Oh goodness. What do you mean you don't know what you do? You're a doctor. You should know exactly what you do. Okay. To solve this, researchers from Yale University School of Medicine genetically engineered adult mice, of course, so their heart nerves would glow, of course, making them much easier to study, obviously. Duh. After locating the nerves. See, that could be its own article. It's not necessarily revolutionary at this point, but like, Just stated so nonchalantly. I guess nonchalant is the proper adjective. After locating the nerves easily, the team analyzed which genes were active in them. They discovered that the nerves fell into two categories, which they called NPY neurons and DDAH1 neurons. Mapping nerve pathways. To determine their exact roles, the researchers traced their pathways across the heart using 3D imaging. The images revealed that both groups were wired to completely different areas. Speaking of bilateral differences, like those discussed in the last video. Maybe not. When the study authors tested the NPY neurons, they found that stimulating them slowed the heart. But when they destroyed the population of cells, heart function rapidly deteriorated, ultimately leading to death. This suggests that these nerves are vital for keeping the heart beating. The ICNS is not merely modulatory, but is essential for cardiac performance and survival, commented the study authors in their paper. The picture of the DDAH1 nerves was less clear-cut. Neither stimulating nor destroying them seemed to make any difference under normal conditions, and the mice survived. However, the Yale scientists did discover something fascinating about the DDAH1 population. When they put the mice through a physical restraint stress test, these cells suddenly activated to protect the heart. Without them, the intense stress caused the heart to develop fatal electrical instability and sudden cardiac arrest. DDAH1 plus ICNs are essential for maintaining cardiac stability under extreme physiological or psychological stress, they wrote. Future treatments? Understanding this division of labor could fundamentally change how doctors treat cardiac issues in human patients. The team noted that problems within this network of nerves are linked to major human heart conditions, such as atrial fibrillation, heart failure, and sudden cardiac death. Therefore, understanding exactly how these distinct cell types work could potentially lead to treatments for some types of heart problems. Ooh. Very hearty. Now, first, first 3D nanoscale maps of human airway epithelium reveal hidden architecture of lung defense cells. Researchers at Queen Mary University of London and University of Cambridge, in collaboration with colleagues at HHMI, Janelia, and NIH, have created some of the most detailed three-dimensional maps ever generated of human airway cells, revealing how the specialized cells that protect our lungs are built and organized. The study, published in Cell Reports, combines advanced volume electron microscopy with super-resolution light microscopy to reconstruct individual airway cells in 3 dimensions at nanometer resolution. The work provides an unprecedented view of how the internal structures of human cells are organized as airway cells mature and acquire specialized functions. Our understanding of cells has traditionally relied on looking at thin 2D slices or individual molecular components, said Dr. Vito Manella, reader in nanoscale biology at Queen Mary University of London and senior author of the study. Oh, a reader. That's probably an actual position I haven't heard of yet. Can't chill too hard. That is both a boundless limit and advice. Now, by reconstructing complete cells in 3 dimensions, we can now see how the different parts of a cell are arranged and connected, providing a much more complete and time-resolved picture of how human tissues are made and function. The nanoscale maps have the potential to provide a better understanding of respiratory diseases. Many lung diseases, such as asthma, chronic bronchitis, and chronic obstructive pulmonary disease, involve changes or damage to airway cells. By comparing diseased cells with these healthy reference maps, researchers could pinpoint exactly what changes occur, revealing early warning signs and mechanisms of disease and providing new treatment targets. There is also a video in this article, so I do recommend actually visiting the page. A new way to see human cells. The airway epithelium, the thin layer of cells that line the inside surface of the respiratory tract, forms the first line of defense against the external environment, continuously protecting the lungs from inhaled particles, pathogens, and pollutants. Nice alliteration. To perform this role, airway cells undergo a highly organized process of differentiation, developing specialized structures, including motile cilia, motile, model, M-O-T-I-L-E, model. The microscopic, hair-like structures that extend from the surface of certain cells, which help clear material from the respiratory tract. Until now, it has not been possible to follow this process, capturing the complete 3-dimensional organization of the cell and its internal components. The researchers combined large-scale 3-dimensional volume electron microscopy with AI-based segmentation, super-resolution microscopy, and CRISPR-Cas9-Ko approaches, allowing them to connect information across different biological scales, from entire cells and organelles down to the function of specific molecular structures. This multimodal approach revealed unexpected complexity and plasticity in the architecture of airway cells and uncovered previously unrecognized relationships and physical contacts between cellular structures involved in building and maintaining the machinery required for airway defense. A publicly available resource for the scientific community. All right. A key outcome of the study is the creation of an openly accessible digital resource generated in collaboration with the Enhanced FIB-SEM Imaging Shared Resource at HHMI Genelia. The resulting nanoscale datasets will be made available to researchers worldwide through the CellMap initiative, supporting broader exploration and reuse by the scientific community. The datasets will also be linked with the lung map and the EMBL-EBI cell ontology efforts, allowing these nanoscale maps to be integrated with existing molecular and cellular reference resources. These are not simply images. They are detailed digital representations of human cells that can be explored, analyzed, and reused by scientists around the world, said Manella. By making these resources openly available, we hope to accelerate discoveries in lung biology, respiratory disease, and the development of new computational approaches for studying human cells. Amazing. I very highly recommend checking out this video. Link in the description. Now, tracking ion movement in porous carbon electrodes to boost energy storage and water desalination. A new study by researchers from Leipzig University, Friedrich Schiller University, Jena, and the University of Cambridge has revealed how ions move and exchange within complex porous carbon electrodes. These electrodes play a key role in high-performance energy storage, water desalination, gas storage, and other electrochemical technologies. To analyze this complex ion transport, the scientists use two-dimensional NMR exchange spectroscopy, a technique that makes it possible to track how ions move between different chemical environments and how quickly this exchange occurs. They have published their findings in Advanced Energy Materials. Their work addresses a long-standing challenge in energy materials research. Although porous carbons are widely used because of their large internal surface area, high electrical conductivity, and tunable pore structures, researchers have found it difficult to directly quantify how ions move through their pore networks at the microscopic level. A patchwork of pore environments. PORE. In particular, carbon electrodes do not provide a uniform pore environment. Instead, ions move through a heterogeneous landscape. Porous electrodes consist of a solid material containing cavities, or pores, of different sizes. Micropores have a diameter of less than 2 nanometers, 2 billionths of a meter, while mesopores range from 2 to 50 nanometers in diameter. The pores are filled with an electrolyte, a liquid containing freely mobile positive and negative ions that enables the ions to move through the material. To account for this complexity, our research team developed a quantitative analysis approach based on two-dimensional nuclear magnetic resonance exchange spectroscopy, known as 2D EXSY NMR. This method allows us to observe how ions exchange between different local environments over time, explains the study's first author, Dr. Henry R.N.B. Ennefel of Leipzig University's Felix Bloch Institute for the Solid-State Physics, adding that the approach goes beyond conventional simplified models, providing a more realistic picture of how ions move within porous electrodes. Where ion exchange speeds up. The study used aqueous Li TFSI electrolytes. These electrolytes, which contain the lithium salt LiTFSI and enable lithium ions to move between the electrodes, were confined within two porous carbon model materials, CMK3, a mesoporous carbon with predominantly one-dimensional channel-like pores, and STCMK3, a hierarchically structured carbon. The analysis revealed different exchange regimes, ranging from rapid exchange near the surface to slower diffusion within the pores. In the hierarchically structured carbon, the team also identified additional transport pathways between different pore environments. This demonstrates how pore connectivity can accelerate ion exchange and improve transport efficiency, says the study's senior author, Professor Rustem Valiulin of Leipzig University's Department of Applied Magnetic Resonance. It kind of makes sense that isn't the exchange would occur faster near the surface, right? Going through different sets of filters. Now, universal structure of exceptional points revealed in nonlinear light-based systems. Exceptional points, or EPs for short, are among the phenomena of modern physics. Among the phenomena. Amazing. These are special points, or locations, at which the properties of matter, space, or time change. In a new theoretical study, researchers from the Institute of Photonic Quantum Systems, or PHOQS, at Paderborn University, in collaboration with researchers from the University of Arizona, have shown that exceptional points in nonlinear systems follow a universal geometric order, something that was previously unclear. Their findings have been published in the journal Nature Communications. Wow. Like low-key hardcore. Right. Exceptional points are points in physical systems at which not only two eigenvalues, but also the corresponding states emerge. Such phenomena occur in so-called non-Hermitian systems. Hermitian, yeah. Which are characterized, for example, by amplification, loss of interactions with their environment. They are the subject of intensive research in fields including optics, lasers, quantum systems, and polaritron condensates. Polariton. There we go. Until now, EPs have mainly been studied in linear systems. In such systems, they can often be described as isolated points in parameter space. However, many real physical systems are nonlinear. Their properties depend on the intensity, occupation, or state of the system itself. From isolated points to structure. We were able to show that nonlinear exceptional points do not follow just any geometry. explains Dr. Stefan Schumacher, whose research group carried out the work. The theor- the theor- ha, the theoretical study was led largely, ha, goodness graciousness, was led largely by Dr. Nai Kwong of the University of Arizona, as well as Jan Wingerbach in Schumacher's research group, and Dr. Laura Aries in the research group of Dr. Jan Sperling, also of Paderborn University. What a network! What a network! Close collaboration with Dr. Rolf Binder and Kwong of the University of Arizona was essential to the success of the work. Commenting on the findings, Wingenbach says, the discovery of a universal cone and cusp structure came as a surprise. It shows that we can now understand the physics of nonlinear exceptional points much better. This is a crucial step toward making targeted use of these phenomena for future applications, for example, in sensor technology or functional photonic systems. Schumacher adds, very different physical systems can exhibit the same characteristic structure in the vicinity of an exceptional point. This universal topology provides a kind of roadmap for identifying such points more precisely in the future, understanding them, and making them usable for applications. A roadmap for sensitive devices. The study offers a new perspective on known linear EPs and demonstrates how they are embedded in nonlinear systems. Exceptional points are considered promising for highly sensitive sensors because systems in their vicinity can react particularly strongly to small disturbances. At the same time, with nonlinear systems, it is crucial to understand what amplification is achievable and where the fundamental limits lie. The new topological description can help determine such limits mathematically with precision and design robust, highly sensitive components, goodness, for various physical platforms. In the long term, the work points to a deeper unity within nonlinear, non-Hermitian physics. Different systems can exhibit the same universal topological signature despite differing microscopic details. Wow. There goes a lot of content. Well, this has been another good news read to you with 5 lovely articles. It has been a pleasure and a joy to read these with you. As always, comment any articles you may want me to consider reading, and I will link these in the description below. Until next time, peace, peace.